Hello. So, please enter your choice. That was a homework assignment. So, right now, you don't even have to think about it. You just recall your homework answer and just press it. '67. So, one of these days, one of the common lectures, I probably just take a picture of the whole class. But the sign-in sheet somewhere in the room, floating around. So please also use it. Okay, 68, 69. You don't really have much time left. Just press anything, okay? I'm gonna add. So if just press anything to confirm. Oops. No. Oops. Yeah. To confirm your presence and the fact that you've done some homework. All right? So this is what we talk about this time, a buoyant force. And remember, the experiment is very clear and simple. I just want to repeat it one more time for the record. Now I'm going to do it with an additional element slightly differently. So that's an empty beaker. It has some mass, but we can neglect it. Now, that wasn't planned. All right. That's water and food coloring. So in the future I might eat it when I'm hungry. While pouring water in this, we can see, of course, it was getting heavier and heavier. Yeah. Now it just tells us how heavy this water is. And the next part of this experiment is simple. We attach a ball to a scale and immerse it. So we've seen what was happening here. Because of the buoyant force pushing up, this reading decreases. This reading has a name, the apparent weight. So everything we read on the scale, that's what apparent weight is. But also, while the top reading goes down, the reading at the bottom, of course, goes up. The Newton's third law tells that if this force changes, that also must change by exactly the same amount of force. So we can again all right. Last time you saw this scale, now you see this scale. We can again, of course, compare the forces before and after and calculate the buoyant force. And no matter what experiment we're trying to conduct, the expression for the buoyant force is always the same, which is this one. It always equals the weight of the water or liquid in general displaced by this object. And if instead of water, I would have used a different fluid, a glycerin, for example, would it change the buoyant force? Well, of course. The same ball, of course, displaces exactly the same amount of liquid because the volume of the ball matters. But because the glycerin has larger density, it would exert a stronger buoyant force. But instead of glycerin, bless you, what we have here is air pushing on this ball. The air is a fluid. But because the density of the air is almost 1,000 times less than density of water, the buoyant force acting on this ball is negligible. It's practically zero. That's why we don't care about it. So, one gram, it can be done both ways, right? 1 gram is 0.001 of a kilogram, and centimeter cubed. 1 centimeter is 1/100th of a meter cubed. That's how many people have it done, and well, turns out 1 times blah 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 0.1, so 0.1. Most of you have chosen this relationship. Either I made mistake or you made mistake. What do you say? Someone has to say something. It's either I made a mistake or you. Which is? Can't hear you. Yeah, what did I do wrong? Prove it. 1. This is what 1 gram is. This is what 1 centimeter is cubed. What's wrong? Yes. Do I? Are you sure? What mathematical symbol do we use if we want to indicate what we wanted or doesn't want to cube or square? There is a specific mathematical symbolism we use, which is what? Yes. Parentheses. So you should have screamed, parentheses, I don't see them, that's it. So you don't see parentheses, and that was a wrong calculation. Now, when you see parentheses, PEMDAS, right? 2 parentheses first. Now, that's what it means, but only because of the parentheses. And that, of course, changes everything. It changes everything. So, 1,000 kilograms per cubic meter or 1 gram per cubic centimeter, same density. The first number, again, tells us how heavy 1 cubic meter of water is. That number tells us how heavy 1 cubic centimeter of water. A centimeter is this big, less than 1/2 of an inch. So if you take a cube like that, pour water in it, put it on a scale, you will read 1 gram. That's it. Nothing special. Now, any problem related to a buoyant force is not a new problem. It's a very old-fashioned, perfectly studied problem on static equilibrium. Not complicated. when we need to use the torque. No, simple version, when net force equals 0. But to solve that problem, this is what you have to do. You have to draw a free body diagram for any possible situation. Of course, you have to show the buoyant force, but you also have to show all other forces possibly acting on it. For example, here we have force of gravity, and here we have force of gravity, and where else? Normal force. And this normal force has the same magnitude as the apparent weight. Here, we of course have force of gravity, and where else? The force of tension. And that tension, again, has the same magnitude as the apparent weight. Now, if it floats and we don't want to, we can push on it or add an additional mass to it. So in that case, well, if we push, we have to indicate, well, a force of gravity and that additional force which we might apply to it. So as long as you have a free body diagram correctly drawn, that's it. The rest is, well, just solving for whatever force you need to solve it for. And of course, you have to use the equation for the buoyant force. You may want to use sometimes equations for additional forces. For example, if instead of a rope you have a spring, you may want to use expression for the elastic force, which is, again, not a new expression. It's just spring constant times the elongation or contraction of the spring. All right. So I'm going to give you literally like 7.5 seconds. So, and you have to practice. This picture looks like the very first picture on this list, so you have to recreate the free body diagram. And, well, in general, how would I know? I read the same slide you read. This is all I want. This is all I know, you know. So you have to calculate the magnitude of the buoyant force. I promised you 7.5. Yeah, okay. Close enough. So again, you read this name, a buoyant force. And you have two options. Number one, you should relate the buoyant force to all other possible forces, and because everything is in equilibrium, net force has to be equal to 0. And number two, you can use the expression for the buoyant force, density of the liquid times the volume which this ball displaces, times g, or both, whichever works. You know, if one doesn't work, you try another one, and well, that's exactly what you should do. In this situation, all you have to do is just set two magnitudes together, because the buoyant force must have exactly the same magnitude. Which expression did I use? This one. Because the ball floats in equilibrium, net force has to be equal to 0. In order to net force to be equal to 0, buoyant force must have exactly the same magnitude and opposite direction to the force of gravity. That's why a ship floats, even a warship, huge one, which weighs millions of tons, but still doesn't sink, right? Because the buoyant force compensates force of gravity. And this. So I'm going to give you some time to solve this problem, not for the density, for the mass. M equals, I will measure dimensions, and this is water. If I know the dimensions, I can calculate the volume. If I know the volume and the mass, I can calculate the density. So eventually we can go down to the density, but still, one of the first calculation should be the mass. And I want to give you some answers before I switch to the camera. So you should write those answers. 0.250, 0.5, 1, 1.25, 1.5. Well, hopefully one of these is correct, but just in case, none of the above. So take a photograph. And I'm switching. So maybe add some more water. This is my cylinder. So you can write down the dimensions. I can read you the diameter. Well, 7 centimeters good enough. 7 centimeters the diameter of this base, and the length 16 centimeters. All right. Now I put it into this tank, pool, and it floats. See, it doesn't touch the bottom of this. It floats. So I can straighten up a little. Where does it go? And I can measure how much of this cylinder is above the water, above the surface of the water. It's about 4 centimeters. So again, the diameter was 7 centimeters. This part was 4 centimeters, and total length was, what did I say? 16, 17? 16.16. So that means below we have 0.12 centimeters. And that's it. So now, either you solve this problem and you choose the correct answer, or when time running out, you just choose the answer. Hopefully it's correct. I want to calculate the volume of the whole cylinder. when we know the mass, calculating the density is a simple calculation. So the volume has to be equal to the height times the area of the base of the cylinder. So 0.16 times pi r squared, pi 0.07 divided by 2 squared. That should give us cubic meters. Of course, it has to be a relatively small number in cubic meters. This is this should be a very small fraction of a cubic meter, right? 0.16 times 3.14 times can't see anything. 0.00002 cubic meters. Well, 0.00002 times, sometimes just to get the feeling, just for us, it's convenient to convert into cubic centimeters, as we know, like 1 cubic centimeter is, this big, so this should be like, I don't know, dozen, 2 dozen cubic centimeters, something like that. So 1 cubic meter is equal to how many cubic centimeters? Someone should say a word. And the answer to this question is a single word. How many cubic centimeters in 1 cubic meter? Well, you either know and say, or not know, don't know, and calculate. That's it. So you can't just sit motionless, Either you're speaking out or you're calculating. Those are the only options. So? No, not to the third. What did you say? Yeah. What did you say? 1 million. 1 million. A million. So it's 10 to the 6th. This is how a cubic meter looks like. Looks like 100 centimeters each side. So if you multiply 100, 100, 100, that gives you 1 million, or 10 to the 6th. So 1 million. 1, 2, 3, 4, 5, 6, 20 cubic centimeters, which is about right, yeah. Again, if this is 1 cubic centimeter, so about 20 you can fit in this jar. Well, but that's not what we're looking for. What did you say about the mass? 0.5, most of you. 0.5 is a correct mass, is a correct result. And again, this question is not related to the expression for the buoyant force. It's related to the fact that when it floats, the buoyant force must cancel the force of gravity. So what just happened? The density of water, 1,000. How much? What volume should we use for calculating buoyant force times 10? That G has to be equal to M times 10. So 10 and 10 cancels. So the mass is related to the volume we have to use. And here, which part? Well, in general, we have to choose from 3 options. We can use either whole volume or that part which is above the surface, or that part which is below the surface. If you know which volume to use, you're all set with buoyant force. If you're still not sure, solve more problems. So what volume should we use? Top? Hull? Bottom? Bottom, yeah. So all we need to do is just calculate that, well, which is pi times radius squared times the height of that part, which is 12 centimeters. Well, yeah. And I know it has to be 500 grams because that's what I put in it. Of course, it's empty. So the mass of this plastic can is practically zero. But if I put a 500 gram weight in it, the whole thing weighs 500 grams, a half of a kilogram. Oops. So that's how I know it has to be 0.5. Any questions? And the density we're calculating is not the actual density of this thing, it's the average density. Because, of course, the weight, which is inside, takes only a small part of this volume. The most of the part is empty, well, air. So the average density will be equal to 0.5 divided by the total volume. Or easier, using grams per cubic centimeters, 500 grams divided by 20. 25 grams per cubic centimeter. No, 2.5. I'm sick, so I can't think clear. 0.20, it's supposed to be less than 1 gram per cubic centimeter because it floats, less than water. It's supposed to. Where am I? Less than 1 gram. Okay, so we know that we may have only 3 options to choose from when we need to compare a density of an object and the density of the fluid. Yeah. Object has the same density as fluid. The object has, well, higher density than a fluid, and the object has lower density than a fluid. So this is what we call an equilibrium. It's like a submarine floats. The average density of the submarine should be equal to the average density of the seawater around it. And if the density, the average density of the object is greater than the density of fluid, it sinks, goes down to the bottom. But if the average density of the object is less than, it rises to the surface. And that's how they maintain, submarines, manipulating the height of the submarine. Here, the apparent weight. Well, we know the apparent weight is that reading we observe on a scale. So basically, that's what we're looking for. If we calculate tension, that's it. The free body diagram is here. So what do? Well, the buoyant force plus tension should cancel gravity. So the apparent weight we're looking for, which has the same magnitude as that reading, should be equal to mg minus buoyant force. M is 0.7 kilograms, G is 10, buoyant force. Since it's water, the density of water 1,000 kilograms per cubic meter. Since it's a ball, a sphere, the volume will be equal to 4/3 pi r cubed. And diameter is 10 centimeters, so 0.1 of a meter divided by 2 gives radius. We should cube it. and times G. That's it. So 0.7 times 10 is 7. And here, I don't want to run the exact calculation. You can do it for your homework. But to make a rough estimation, I can cancel pi and 3, 3.14, 3, close enough. Now 0.1 cubed and 10,000 also cancel each other out. So what's left is 4 times 8, 40. 4 times 10 divided by 8 because 2 cubed. So it's going to be 7 minus 5, 2 newtons. So it's all about drawing a free body diagram, setting net force to be equal to 0, and follow the lead of the values given to us. What if only a part of this ball is inside? So we're moving it up, and eventually this picture looks like this. A beaker, water, same tension here, but now 2/5 of the ball is outside. We don't care, strictly speaking, about how much of it outside. We care how much of it is inside. So if 2/5 is outside, inside the water below the surface is going to be 3/5 of that. So that's the volume we call the volume of liquid displaced. It's going to be equal to 3/5 of the total, which is 3/5 times, okay, one more time, pi, it's same ball. So now, again, now this, 0.1 cubed 10 to the negative third, and here we have 12, here we have 10. 12 over 10, 1.2. 1.2 cubic meters, that's it. That's the only new calculation which had to be done. The force of gravity is still the same. The buoyant force now will be different. So the tension will be different. And tension plus the new buoyant force will be equal to the old force of gravity. So the new tension, which is the new apparent weight we're looking for, will be equal to same force of gravity, which is 0.7 times 10, minus the new buoyant force, which is equal to 3/5 of the old buoyant force. If the volume is 3/5 of the old, the buoyant force will be equal to 3/5 of the old, and that was equal to 5 newtons. So 7 minus 3, 4 newtons. Apparent weight is a force, so we have to use newtons. And of course, when it's completely submerged, we saw it. There is one reading, but if it's partially submerged, it's going to be a different reading. The buoyant force is not strong anymore, so the apparent weight will be closer to the actual weight. Here, well, first of all, what's happening? You see, now the ball has density less than density of water. So without this string, it would float, rise to the surface. So if we cut the string, that's it. So basically, all we have to do is just, again, draw a free body diagram. We still have a buoyant force pointing up. We still have force of gravity pointing down. And that's the tension due to that string. It's not a post, it's a string. So if I cut it, it goes up to the surface. And that's, again, what we're looking for. The apparent weight is equal to the tension. So now to calculate the apparent weight, this is what we need to do. Previously, it was gravity minus buoyant. Now it's buoyant minus force of gravity. So nothing well, starting from this, nothing is different. It's density of water times the volume 4/3 0.1 over 2 cubed times G minus 0.3 times G, whatever it is. Actually, we have too many variables given. I believe what meant to be done is this. If we know the density, and if we know the density and if we know the volume, we actually can calculate the mass. So that should be an extra calculation. So that should be the density of the ball, 0.8, times the volume of the ball. It's completely submerged, so it should be total volume 0.1 over 2 cubed. And now times G times 10. Okay. Okay, this is an important situation. Very briefly, it's very similar to the experiment we've done before with the cylinder. It's the difference is now we don't have exact measurements. We know that 25, the density of this material, the density of this, let's say, block B, yeah, is 25% less. So we don't even know if it's water. How do we write it? Well, what does less mean mathematically? Have to subtract. So this is the density of this liquid, and we have to subtract 25% of that, which gives us 75% or 0.75. So this sentence has to be written mathematically. The density of this material is 0.75, the density of the liquid, which keeps it floating. That's it. The rest is simple. Again, because it floats, the buoyant force and force of gravity should have same magnitudes. So for the mass of this object, we should write the density of the object times the total volume of the object, box, times G, and the buoyant force should be equal to the density of the liquid times that part of the volume which is equal to the volume of the displaced liquid times G. In many situations, we can see again and again G canceled. So this is what we're looking for. What part of the block is in the liquid? What part means what percentage? So that's the ratio we need to calculate. The volume displaced over the total. And if we solve it, that's going to be equal to the ratio of the density of the material for the block divided by the density of the liquid. And we know this density, or this ratio, is equal to 0.75. So 25% of this box will be above the surface and 75% of this box will be below the surface. And we can ask an additional question. If I want to be completely submerged, either I have to push on it with my finger to make it move deeper, or I can add some extra mass. So in that case, the question is, what is the amount of that extra mass we should add? Well, if we add that extra mass, the system is in equilibrium still. It's just a new equilibrium. So the force of gravity now will be equal to the total mass of both objects together. And that should be compensated by the buoyant force. And the buoyant force should be equal to the density of this liquid times, now, because this whole block is below the surface, that just should be the volume of this whole block times G. So again, cancel G, cancel G. What we're looking for is the big M, and big M will be equal to this, the density of the liquid times the total volume of the box minus little m, and the little m, the mass of this box, equals the density of the material the box made of times the same total volume. And we know some extra variables here. This is water, so 1000 minus, this is 75% of the density of water, so 750. And the volume is 8,000 cubic centimeters. So 8,000 times 10 to the negative 6 cubic meters. That's it. So every time we're using the same strategy. All right. I'm going to do this experiment. You choose your answer, because I'm going to switch to the camera very soon. Right now. So I just want to show you what's happening here. See? This is like a boat in a lake. That heavy weight inside the boat is 2 kilogram weight, 2 kilograms. And you can mark where the water level is now, right here. So what I'm going to do, first I'm going to take it out, not the boat, just the weight. So of course now the level drops, and final action, which I'm going to do, I'm going to take this weight and I put it now in this pool. Of course, it's going to sink. It's heavy, yeah? And the force of gravity, 2 times 10 to 20 newtons. The buoyant force is not strong enough to keep it from sinking. The question is, what's going to happen to the level? What's going to happen to the level? Now, since you know what the question is about, you don't need to read all these possible answers. You just need to choose yours. So again, what we compare is this level. I really have to keep it in the middle, otherwise it capsizes. So this level with a new level, and the new level is happening now. So now we can compare the answer you've chosen with the reality. So if I wonder how many of you chosen correct answer. What do you think? Raise your hand. None? Oh, 1, 2. Well, of course. Again, it sinks. It means that the buoyant force acting on this only is much weaker than the buoyant force needed. Okay, come on. Than the buoyant force needed to keep it from sinking. So right now, of course, we need much stronger buoyant force acting on it. Much stronger buoyant force requires much more liquid displaced. That's why when I do this, the water level practically doesn't change. It stays below the original level. Okay. The water level stays the same. That was the most popular answer, which is wrong. The water level rises, which is wrong. And, well, turns out, yeah, that's about right. How many people? Well, I assume because that's wrong, that's wrong, that's wrong, even if I can't read what was, that's supposed to be the correct. Let's see. Yep, false. So if we draw these two pictures, if I take this picture and I redraw it right here, what should we see? This, the new level. Well, you saw what was happening when I was pouring water into this beaker. The scale reading, of course, was increasing. More mass, more force of gravity. So, question is, if I have exactly the same amount of water in this, but I use two different beakers, one is wide, second is narrow, does it make any difference? Well, it depends on what we mean by difference. Here, the acting surface is much smaller. Here, the acting surface is much larger, but the force they provide to the scale is the same. Same amount of water, I just pour it from one beaker into another. What is difference? Well, force, we can say force distribution is different. And how do we call that physical parameter? This is how. We call it pressure. Why is it important? Well, sometimes it is, sometimes it isn't. Let's do a simple experiment. So this is an official definition of what we call pressure. Pressure, that's a force exerted on a square meter of surface. That's it. Just salt. So this is a 500 gram weight. You know, we measure it. This is a 500 gram rod. Now, if I take this weight, I place it, and I let it go. Nothing. If I take this rod, I place it, and I let it go. You see, it sinks deep in it. They exert exactly the same force because mass is the same, mg is the same, but the force distribution is different. So they provide different pressure, and that matters. For example, if you want to walk on snow, what do you use? Snowshoes. Why? Because you distribute your weight over larger area. Or if you're a fan of ice fishing, if you walk, that's dangerous. But if you crawl, you might survive. Or not. All right. We'll pick up from this slide. Thank you. Just in case, I want I want to remind you again, I've sent an email that the lab this week will be downstairs, will take place in a different room, B23. Yes.
How many labs? It's best 7 out of 9, 7 out
Yes.
of 8.
7 out of 9.
Okay, thank you.
What do we do? This is what we do.
My normal lab time is tomorrow, but I can't make it. I have a performance. Do I have to? Can I just show up to any other lab, or do I have to email the TF?
You can.
Or also,
Sure.
if I haven't missed one, that means I could technically miss one lab, right?
Technically, yes.
Okay, but if I wanted to go, I'd have to email the TF.
No. You should just send me an email,
Okay, okay, thank you.
and you should tell the TF what you just said.
Okay,
And make sure
my usual TF or the new TF that I do.
the new TF.
Okay,
And you should make sure, ask him that he would enter your grade.
okay, thank you.
Did you pick up your exam? Oh,
Oh yeah, no, I have it.
it's in this pile.
Okay.
Yes. Yes. Yes.
Thank you for this.
that separately.
But we can take the cont first.